This video is going to look at absolute extrema. And really what we're looking at here is the absolute extrema are the points on the graph in a particular interval where you have your highest point, which would be your absolute maximum, or your lowest point, which would be your absolute minimum. And here we have three cases we want to look at. And the first case we want to look at is on the interval for this graph from 1 to 4. And notice because of the brackets here, this is a closed interval, so we have solid dots as our endpoints. And if we're identifying where is the absolute lowest point on the graph, well, if we look closely, we can tell that right here at the bottom of the curve, this would be our minimum point. Okay, so that's your absolute minimum. So that's one of our extrema points. Do we have an absolute maximum? Well, the maximum would be this point here at the top. So we have a minimum and a maximum. Now, sometimes you need to be careful with the terminology. Sometimes they just say find the extrema, and that means you're looking for your extreme values, your absolute max and your absolute minimum values. A lot of times I'm going to use the word absolute just so that you're aware of what we're looking for. The next example here, if you notice, we have parentheses, so this is what's called an open interval, and that's why we have the open circles here. So that means we never get to this endpoint. We can always keep picking numbers that are closer and closer, so we'll never get to the end. So in other words, that's why it's called an open interval. So now we want to look at, do we have an absolute minimum? Well, of course we have absolute minimum at the bottom, same as before. Do we have an absolute max? And if you look closely, we don't have an absolute max because keep in mind, as we get closer here to this point, we can just always get closer and closer. It's not a closed interval, it's open, so we can never get to a stopping point, and that's why it's called an open interval. So in this case, we only have an absolute minimum. All right, our last example here, we look at, again, we have a closed interval from 1 to 4. So from 1 to 4, again, we have our endpoints. We have a solid dot. Do we have an absolute minimum? Well, if you notice this time, there's an open circle at this lowest point. So here we have no minimum. And once again, this highest point here, because it's a closed interval, this would be our maximum point. Okay, so you'll notice that you won't always have a max or minimum point unless you have a closed interval. So if you have an open interval, it's possible that you will not have a max or a minimum. But if you have a closed interval, such as this first example, you will always have at least a max and a minimum point. All right, the next topic we want to look at here are our critical numbers. And critical numbers occur when our derivative at a point C, so in other words, if f prime of C is equal to 0. So if there's a point on the graph where that point is equal to 0, the derivative is equal to 0, or if the function is not differentiable at a point on the graph C. Now keep in mind the function has to be defined at this point C. So if we look here below, we have a graph. Where is our derivative of this graph going to equal 0? Well, keep in mind the derivative is the slope of the graph, and the slope of the graph, if that's 0, remember that's where we have a horizontal tangent line, and we're going to have a horizontal tangent line right here where our graph changes directions, where we would have a slope of 0. So that means your derivative at this point is 0. So this point here would be a critical number. Okay, so your critical number would occur here at this particular value. And notice again, we would actually have another critical number here because once again, we have a horizontal tangent line at this point where the derivative is going to be equal to 0. Okay, so that's this first part. We have a critical number anytime the derivative is equal to 0, or if our function is not differentiable at c. Well, in the second graph, notice this point here. Do you recall why this point is not differentiable? Well, here notice we have a sharp turn in the graph, and our function is not differentiable at this point. So this would also be a critical number. Now we're going to use this idea here of critical numbers to help us with finding our absolute maximum and minimum points. So keep in mind if the function is not differentiable at a point, or if the derivative is equal to 0, that's a point that we could have a critical number. All right, let's look at the example here kind of algebraically. We want to find the extrema. And once again, a lot of times the directions will say find extrema, and really what that means is you're looking for what's called the absolute extrema. So now we know the extrema can occur based on the examples above. Our extrema can occur at our endpoints of our interval, or also at kind of a valley, or if we had the graph upside down, it could occur at the peak somewhere within side of the interval. Now keep in mind this point that we found here as a minimum in this first graph, this point would have been a critical number because at this point we would have had a horizontal tangent line. So the steps for finding your absolute extrema, well, the first step is we want to find the derivative and locate any critical numbers. And our critical numbers are basically going to show us where we could possibly have a peak or a valley where our graph is changing directions. So if we take the derivative of our function, hopefully this is straightforward, x cubed becomes 3x squared minus 6x. Then we're going to take and set the derivative equal to 0. Remember, we're looking at where the derivative is equal to 0, so now we simply solve for x. So we're going to factor out an x, and we would have, well, let's see, we could actually factor out a 3x, and we would have x minus 2. And if we set each factor equal to 0, we're going to end up with 3x equals 0, x minus 2 equals 0. So if we divide by 3, x is equal to 0. Move the 2 over, x is equal to 2. So here we have our critical numbers. Okay, the values of x that make our derivative equal 0. Now, if we look at those critical numbers we found, where x is 0, well, over here at the right I have the graph of our function. And when x is 0, our critical number is right here. And when x equals 2, that would be this point here. So there's our two critical numbers. And notice we would have a horizontal tangent line at those 2 points. Now, if we look at the entire graph, we're looking at finding the absolute extrema, but we're only looking within the interval from -1/2 to 4. So I've marked off here's -1/2 to 4, and we have a solid dot on both endpoints because it's a closed interval. So we want to now determine where will we have a maximum point and a minimum point. Now, I'm sure you can look at this. If you're looking at the graph here, we can easily tell which point is going to be the absolute max and which one probably is going to be the absolute minimum. And we want to double check this algebraically. Now, from looking at the graph, we could probably go out and say this point way up here is going to be our maximum point, and it looks like this point within inside of this interval is going to be our minimum. So how can we verify that? Well, if we take our critical numbers that we found and our endpoints up here, if we take our endpoints, negative 1/2, and plug those into the original function, f of negative 1/2, you would have negative 1/2 cubed minus 3 times 1/2 squared. And if we calculate f of a negative 1/2, we end up with a negative 0.875. All right, then we want to evaluate the other endpoint, which is f of 4. So you're going to plug 4 in. So we would have 4 cubed minus 3 times 4 squared. And that's going to be equal to 16. And now we want to check and evaluate our critical numbers that we found when we set the derivative equal to 0. We had x equals 0, x equals 2. So now we're going to plug 0 and 2, both of those into the original function. So f of 0, well, that's going to give us 0 cubed minus 3 times 0 squared, which is 0. And then if we evaluate 2, we're going to end up with 2 cubed minus 3 times 2 squared, and that's going to be equal to a negative 4. So now we want to compare all 4 of these numbers and say which one is the smallest. Well, the smallest number here would be the negative 4, which would be our minimum. And our largest number is 16, so that's going to be our max. And that corresponds to the points we found over here when our max is going to occur when x is 4, the y value is 16, and our minimum here is going to occur when our x value is 2, our y value is a negative 4. So if you notice that this particular graph, our minimum was within inside of the interval and our maximum point was the endpoint. So once again, if you're trying to find your absolute extrema, in other words, your absolute maximum and your absolute minimum, you simply set the derivative equal to 0, solve for x, you plug all of those critical numbers into the function, you plug in the endpoints, and you simply look for the smallest and largest number. All right, the next example, we still want to find the extrema on the given interval. This time we have a trig function, and for some reason I know everybody panics when we see a trig function, but we're going to do exactly the same thing. This time we're looking on the interval from negative pi over 6 to pi over 3, and if we look at the graph over here, for this particular graph, this graph is going from negative 2 pi to a positive 2 pi on the x, and our y-axis I have going from negative 4 to a positive 4. And if I was to plot the points for the interval here, negative pi over 6 is going to fall right about here, and pi over 3 is going to be right in here somewhere. So this is really the interval that we're looking for the absolute maximum and absolute minimum. So once again, first step is we need to take and find our critical numbers. We take the derivative of our function. So the derivative of secant x, and if you don't remember, you can look on the formula sheet here. Secant is secant x tangent x, And once again, at this point, what did we do above? We set the derivative equal to 0, and now we solve for x. So here we have secant times tangent, so we could set, using the product here, we could set secant equal to 0 and set tangent equal to 0. Now the secant x, remember, that's the reciprocal of our cosine, so that's 1 over cosine x. And 1 over cosine x, is it possible for that ever to equal 0? And the answer is no, because 1 divided by a number will never equal 0, so we can ignore this piece because x will never make this part 0. Tangent of x, where is the tangent of x equal to 0? Well, the tangent of x is equal to 0 where y over x equals 0, and that's going to occur when x equals 0. So this is going to be our only critical number. So when x is 0, that's going to give us a critical number right here. And what's our next step? We need to take our endpoints and plug them into the original function. So negative pi over 6. If we plug a negative pi over 6, we get the secant of negative pi over 6. And you could simply use, excuse me, you could use your unit circle, or at this point, if you want to use your calculator, just remember that you would have to type 1 divided by the cosine of negative pi over 6. And if you do that, you will end up with 1.15. And the other endpoint, g of pi over 3, means we're going to take the secant of pi over 3. Once again, pi over 3, you could look on the unit circle, or we could take 1 over the cosine of pi over 3. And you're going to end up with 2. And now we need to check our one critical number, which was 0. So if we plug 0 into the original function, what is the secant of 0? Well, that's 1 divided by the cosine of 0. And 1 over the cosine of 0 is equal to 1. And now your final step is we want to compare which one of these points is the smallest. And the smallest point here is the 1, so that's going to be our minimum. And the 2 is our largest, so that's going to be our maximum. And if we look, we can identify those. Our minimum here does look like it is definitely the lowest point here. This is our minimum, which would be at the point 0, 1. And our maximum here is occurring at the point pi over 3, 2. Okay, so really, if you're trying to locate these extrema points, then all you have to do is plug your endpoints into the function, have your derivative equal to 0 to find your critical numbers, and plug those into the original function, and just simply look at which is the smallest and which is the largest number.